Hello everyone, welcome to my live presentation. My name is Maliheh Mahdavi Sefat and today I discuss Introduction to Deep Learning with Neural Networks, MultiLayer Perceptron. Uh, at the bigger picture, we have artificial intelligence. Inside that is machine learning, and inside machine learning is deep learning. AI, artificial intelligence, is the broad field of creating systems that can perform tasks requiring human intelligence. It has many samples and use cases, like the chatbots we interact with today, and image generation, video generation, autonomous vehicles, and things like that. And then there's machine learning, which is a subset of AI, where systems learn patterns from data to make decisions without explicit programming or instructions. The examples we saw in previous presentations, like the medical diagnosis and recommendation systems. And at last, we have deep learning, which is a subset of machine learning that uses multi-layered neural networks to learn from large complex data sets. And its use cases are the facial recognition, self-driving cars, and language translations, and so on. So we have the machine learning, which is the training a computer to learn how to perform a task from the data itself. And deep learning is training artificial neural networks like that with multiple hidden layers, such as these. The word deep refers to the number of the hidden layers of neurons. Deep layers learn underlying features from raw data, features that are often hidden from or unintuitive to humans. In multi-layer perceptron, which is the general form of neural networks, uh, we have the unit of perceptron, but it's not the classic perceptron. MLP actually doesn't use the classic perceptron. Despite the name, it doesn't use perceptron learning rule or step function. It uses continuous differentiable activation functions and loss function activation functions and loss functions such as mean squared error or cross entropy, similar to Adeline, not perceptron. But the perceptron we're talking about in MLP is something like that. We have the layer of inputs, x1 to xm. Then we have the weights, w1 to wm. We calculate a weighted sum of those inputs, x multiplied by w. Then we have a nonlinearity function to get our output. The formula, mathematical formula is like this. We have the bias that we add to the weighted sum of x and w. If we consider that the x0 could be equal to 1, then we can take them inside the summation notation. And then we have the G nonlinear activation function. This helps to have nonlinear neural networks that can perform more complicated tasks with the real data. If we consider that the W's and X's are vectors, then we can write them with vector notations, capital X and capital W, like this. So from now on, when we say a neuron or a unit, we mean the summation and the activation function. So here in this schematic, each of these circles are the summation and activation, and then the arrows are the weights. The purpose of activation functions in the perceptron that we use here is to introduce nonlinearity in order to work with real-world data sets that are nonlinear. For example, we have the sigmoid that works well with probabilistic models for tasks like classification. The sigmoid function maps any value to 0 and 1, the range of 0 and 1. Here's the sigmoid function and its derivative. Then we have the hyperbolic tangent that maps any value in between -1 and 1. And we have rectified linear unit. It outputs 0 for all the negative values and the linear value, same linear value for positive values. It has only one point of nonlinearity. So, MLP. In MLP, or multi-layer perceptron, the first layer of neurons is typically considered the input layer, representing the input features. The number of units in the input layer corresponds to the number of features in the dataset. If we have 10 features, then we have 10 units of neurons in the first layer. The last layer is the output layer, which produces models prediction, often a classification or a generation result. The number of units in the output layer depends on the number of classes in the classification task. Or, for example, if the task was image generation, the number of pixels in the image that we want to generate. So the number of neurons in the input and output layer are bound to the problem definition. But the number of hidden layers and the units within each layer is flexible, allowing the model to adapt in complexity depending on the problem. So if we want to solve a much complicated problem, we add number of hidden layers or the neurons in each hidden layer. Here's what forward propagation works, and this is the structure of neural network. The same MLP is just shown vertically here, but it doesn't matter. The first layer is input layer here. In input layer, the data enters the network through the input layer of neuron. Each feature in the dataset corresponds to one unit in this layer. And then there's hidden layers. Each neuron in a hidden layer receives input from the previous layer. If it receives all the outputs of previous layer, like this picture, then it would be called a dense layer. It calculates a weighted sum of those inputs, adds a bias, and passes the result through an activation function like ReLU or sigmoid to the next layer. This transformation here introduces nonlinearity, helping the network learn complex patterns. As we said, each of these outputs works as input feature for the next layer. These features are the features that are learned from the data or extracted from the data. Often humans don't have access to these features and cannot imagine or as we said are unintuitive to the humans. The features are hidden in the hidden layers. The output layer is the last layer, produces final prediction, which must match the format and constraint of the task. For example, the number of pixels in image generation or classes in classification function. Earlier layers, the previous layers, are for feature-informed transformation, while the last layer must produce interpretable results. Therefore, the activation functions of the output layer depend on the task. For instance, we have softmax for multi-layer classification, or sigmoid for binary classification, or linear for regression tasks. Then there's the prediction. The output of each epoch is the network's guess based on current weights and biases. This prediction is then compared to the actual label to calculate the error loss, which is used in backward or back propagation to update the weights during training. So we get the vibrate and compare it to the y that is wanted or desired. And then we have the loss. And with loss, we calculate the cost function. Training in a neural network means finding the parameters that yield the best result or the least cost. The data propagates forward, as you can see in this animation, extracting complex features on its way. So here, the output of these hidden neurons are complex features. The loss is computed at the end, and its gradient propagates backward, adjusting the weights and biases using the chain rule. And this is the chain rule, if you remember from the high school calculus. The derivative of f uh, with respect to x, if the f is f of g of h of u of v of x, would be the derivative of x, f with respect to g, multiplied by the derivative of g with respect to h, times dh on du times du on dv times dv on dx. So this is the chain rule that is used in the backward propagation to calculate the gradients of each set of weights. Again, about the loss optimization. We have the J cost function, and we want to find the argmin of that. Argmin means the arguments of the minimum, those weights that result in the minimum J. If we imagine that we only have two weights, W0 and W1, and to be honest, we cannot imagine more than 3D images. So our cost function would be a surface like this, a bumping surface like this with highs and ups. We want to find those set of weights that result in the least cost. For example, in this point. What do we do here? We do this. We compute the gradient at each point. Okay. At first, we initialize the weights randomly. We pick a point by random. At that point, we calculated the gradient. The gradient is the partial derivative of cost function with respect to those weights. The gradient shows the direction that increases the cost. So we need to go the opposite direction. We take a small step the opposite direction of gradient, and in the new points with the new set of weights, we again calculate the gradient, find the direction that increases the cost, take a step in the opposite direction, and repeat this step until we reach the minimum. We hopefully reach the minimum. The formula of updating weights is like this. We calculate the partial derivative of cost with respect to those weights at the moment. This eta learning rate is that small step. It determines the pace of updating the weights. And this negative notation is for taking a step opposite the direction of gradient. And we deduce this term from the weights to get the new weight. After we converge, or the algorithm converges, it returns the final weight. Here's the backward propagation in its structure and how it works. In backward propagation, we update the weights via computing gradient, what we talked uh, just now. It works like this. The loss is computed at the end of each forward pass. These may seem repetitive to you, but that is because I learned in epochs. Whenever I learned something new, I made a new slide. So the loss is computed at the end of each forward pass. Then its gradient propagates backward, adjusting weights and biases using the chain rule. And here is the chain rule for this image. The loss formulas there are several formulas for loss, such as mean squared error, mean absolute error, cross entropy, and things like that. And the gradient flows backward with the chain rule. Chain rule is applied to compute partial derivatives of the loss with respect to each weight in the weight matrix. Here's what we do. For example, for the W out here, we want dj on d out, which could be calculated like dj on dw hat, y hat, which is the y prediction here, multiplied by partial derivative of y prediction on the w out, the vector of w out. And for the previous layer, we add another term here, dw out on dh2, when we want to calculate the gradient with respect to this set of values. And when we want to calculate the gradient with respect to wh1, the first layer of hidden neurons, then we add this term multiplied by gradient of, or partial derivative of WH2 on WH1. And here again, this is the formula for updating the weights. So the important point here is to remember that all weights are adjusted simultaneously using the learning rate eta and the computed gradient. So the backpropagation is a sequential computation, not updating. The computation happens layer by layer, but all the weights are updated at the same time. Of course, we have more techniques and algorithms for updating the weights beside the basic gradient. For example, we have Adam, mini batch, and momentum, and things like that. This mini batch gradient descent uses small batches for updates, a small batch of samples. And this is actually the topic of the next step. So I wanted to show you some code that we did during the step for this project. This is the handwritten digital data set. It's very famous. It consists of 16 or 8 points, 16 features of X and Y. And we worked on this for the project of this step. If you're interested, you can look at my GitHub. The code is there. And we do classification. It's really amazing. Just with 8 points, we can detect handwritten digits with a pretty much good accuracy, 97% accuracy, and it's amazing. So I encourage you to go to the GitHub and read the code. Thank you very much for watching my presentation.